Hello everyone, this is Dr. Webb. In this video we're going to talk about how to set up double integrals using polar coordinates. All right, so let's start with an example. So we want to do this integral where we're integrating x over the region, where the region is in the first quadrant and it's bounded by the lines y equals x and y equals x times the square root of 3, and is inside the circle x squared plus y squared equals 1. So let's draw this out, get an idea of what we're talking about. So there's our axes. So the line, we're focused in on what's going on in the first quadrant. Okay. And so the line y equals x, cutting the quadrant in half. Line y equals x times the square root of 3, so that's a bit bigger slope. So that goes up like that. And then we have the circle x squared plus y squared equals 1. And so it cuts through something like that. Okay, and so we're focused in on this region bounded by these 3 in the first quadrant. And so that's that region right there. There's our R. Okay, so if looking at R, R really does not fit in nicely with the types of regions that we've looked at before. If I think about doing vertical lines across here, so that would be integrating in terms of y first. So if I do vertical lines across here, for some places I'm starting off at this line y equals x, and for some x values underneath here, sometimes I'm hitting the other line, but then sometimes I'm hitting the circle. And so if I wanted to do this integrating by y first, I would have to make a cut, break this up into two regions, and based on which region has the right top function. Well, what about going the other way? Well, if we tried to go the other way, I always have the line x equals square root of 3 going here. But if I go across, sometimes I'm hitting y equals x, and sometimes I'm hitting the circle. So same thing, if I wanted to do it integrating x first, I'd have to make this cut at that y value and break it up based on what's going to be the rightmost function. So either way, in terms of the things that we've seen before, we'd have to break this up into two separate integrals. And that really doesn't sound like a whole lot of fun. And so is there another way to do this? And if you notice, this is just a slice out of a circle. And so maybe if we think about our coordinates more in terms of circles, rather than, the x and y, these are rectangular coordinates. Maybe if we had some sort of more circular type of coordinate system, maybe things will work out better. And so this is what's going to bring us to what's called polar coordinates. Okay, so polar coordinates, we're in two-dimensional, so it's still in terms of two variables. The variable r, this is r for radius, and so r is measuring out the distance a point is away. So let's draw out axes, take some point. This is our point here. Call it r theta. Well, what the r is that is the distance the point is from the origin. And so since r is talking about a distance, we're going to say that r is always going to be greater than or equal to 0. There's a couple of occasions where it might make the most sense to let r go negative, but for our purposes, we will almost always focus on r being non-negative. And so that gives us the r part of it. And then theta is an angle, and it's the angle going up from the positive x-axis. Okay, and so this is how we're going to identify our points. It's the distance away from the origin and the angle up from the x-axis. So our bounds that we're usually going to use for theta, there's actually two common ones. Both of them get you all the way around the circle. Just one of them, the 0 to 2 pi, you're starting off on the x-axis, going around counterclockwise, ending up at the x-axis. Another common one is sometimes it makes more sense to, rather than starting at 0, to start at negative pi. And so that starts you on the negative x-axis and go all the way around, hit 0, and keep going around until you hit pi. Okay. And so depending upon where you need your angles to be, usually we pick one of those two coordinate systems, one of those two bounds for theta, sets of intervals for theta to be in. But they both will end up giving you the same thing at the end of the day. Okay, so let's talk about conversions. What if you know your point in terms of x and y and you want to figure out what it is in terms of r and theta? So we have some point up here. We know what its x value is, and we know what its y value is. And we want to be able to figure out what this is in terms of r and theta. Well, in all of this, we're just going to be basically completing a triangle. Okay. And so r is looking at this hypotenuse here. X is talking about the base. Y is talking about the height. And so from the Pythagorean theorem, we get that r squared is equal to x squared plus y squared. And so solving for r, we're going to get square root x squared plus y squared. Okay. Now, to get theta, well, we have to remember that, again, focusing in on the fact that this is a right triangle, theta is this angle right here. Well, tangent of theta is equal to opposite over hypotenuse, and so that's y over x. And so solving for theta here is it's going to be arctangent of y over x. And so these are our conversions from, if you know the x and y values, how to get r and theta. So let's write this up nicely. R is the square root of x squared plus y squared. Theta is going to be the arctangent of y over x. What about going the other way? You have things in terms of r and theta, and you want to know how to express them in terms of x and y. What x and y are in terms of r and theta. Okay, so let's start off with the same picture. And so we have r here, we have theta. Well, again, we're going to just complete in the sides of a triangle. Okay, so for x, x is the adjacent side of the triangle, r is the opposite side. R is the hypotenuse, so we have adjacent and hypotenuse. And so adjacent over hypotenuse is equal to cosine of theta. So solving for x is going to be r times cosine of theta. Y is right here, so y is the opposite side. Y is the opposite, divided by the hypotenuse gives me sine of the angle. So solving for y is going to be r sine theta. Excuse me. R sine theta. Okay. So if we're given r and theta, x then is r cosine theta, y is r sine theta. And so let's write that in. Okay, so these are the conversions we're going to use if we have something written. Typically people tend to write things using x and y, the rectangular coordinates, and so this is how we can go back and forth between the rectangular coordinates and the polar coordinates. Okay, so when would you want to use polar coordinates? Well, usually it makes the most sense to use polar coordinates if the region you're integrating over is a circle or some part of a circle, because those are the types of regions in polar coordinates that look nice. So what do I mean by this? So let's just focus just on expressing a region using polar coordinates. So we're going to look at the region inside the circle, x squared plus y squared equals 4, and above the x-axis. So here's our axes. So x squared plus y squared equals 4. So that's a circle of radius 2 going around like this. And then we want it to be above the x-axis. So there's our region right there. Okay, so if we want to express this in terms of polar coordinates, usually kind of makes sense to maybe start off with r. And so r, remember, is we're thinking about all the way across, how far out do you have to go? Well, since the outside of this is a circle of radius 2, to stay inside the region starting at the origin, we're starting at the origin, so r is starting at 0, and we're just going out until we get to 2. Okay. And now what are the values of theta in which we are taking these radii? Well, if we start at theta equals 0, that gives us the positive side of the x-axis. And then we want to draw positively all the way around until we get to the negative x-axis. And so our theta here, positive x-axis is 0, and we're going up until we hit the negative x-axis, and that's when theta is equal to pi. So our bounds here are theta goes from 0 to pi, r goes from 0 to 2. And if you look, in the bounds here, neither the bounds for r or for theta contain the other variable in them. So this is very much sort of like, in terms of the variables theta and r, it looks similar to just rectangular bounds because there's no dependency on the other variables in them. And so if you remember from, when we started doing integration, these types of bounds are the easiest type to integrate over. So now let's look at the region again in the first this time in the first quadrant, bounded by x squared plus y squared equals 1, x squared plus y squared equals 5, y equals x, and the y-axis. So we've got 4 things in here. So let's start drawing this out. Okay, so we've got 2 circles, x squared plus y squared equals 1. That has radius 1. X squared plus y squared equals 5. That's going to have radius square root of 5, which is a little bit more than 2. And so those are the 2 circles in the first quadrant. Y equals x is splitting the region down in the middle, splitting the quadrant down the middle. And then the y-axis is right here. And so the region that we have in here is right there. And if you look, this would be a really tricky region to try and express in terms of x and y. If we wanted to integrate in terms of y first, sometimes we have this circle on the bottom, sometimes we have this line on the bottom. If you wanted to do it in terms of x first, think about horizontal lines, it's even worse. Sometimes we have this circle as the leftmost and then the line is the rightmost. Sometimes we have the y-axis as the leftmost and the line is the rightmost, and sometimes we have the y-axis and the outer circle. And so that would be a real disaster to try and set up. We'd have to break it up into 3. But in polar, this is going to be quite easy, right? And so going through here, what are our angles going through here? Well, first angle is going through when y equals x. And so if we'd write it as y over x, we get a constant 1. And so what angle has tangent equal to 1? Well, that is pi over 4. And then our thetas then are going up to the y-axis, and the y-axis is at theta equals pi over 2. So our bounds for theta are going from pi over 4 to pi over 2. And then what about our bounds for r? Well, for each of those thetas, we start off at the inner circle, and we go out until we hit the outer circle. And so our lower bound for r is the inner circle, which is radius 1, until we get out to the outer circle, which is radius square root of 5. And so again, you can see these are quite nice bounds in terms of r and theta. And so these would probably be quite nice to integrate with. Okay, so now we need to draw the regions. The last important question that we have to think about is measure. So remember when we built the Riemann function to talk about doing this double integration, the dx dy, well, this was coming from the delta x delta y, which was the base underneath the surface, right? And so this delta x delta y is the area of the base. So the area of the base equals delta x double delta y, and then when we took the limits, that's how it got converted into dx dy. Okay, so we have to think about what little bits of area are going to mean in terms of r and theta. And so really what I mean by that is that if you start at a point, so let's put our axes right here. If we start at a point r theta, what happens when we add a little bit to r and a little bit of theta separately? What type of area does it give us, right? Because deep down, getting this box, if we start off at xy and then I add delta x, and then I add delta y, and then close it off as a box, well, the area created by adding in the delta x and the delta y is exactly delta x times delta y. And so this is where our little change in area is coming from adding in delta x and delta y. Okay, so what if we add a little bit to r? Well, adding a little bit to r, that's going to put us farther out from the origin. And so that's going to put us to the point r plus delta r theta. And so the length of this right here is delta r. Now, if I increase theta by a little bit, that's going to turn us counterclockwise. And so if we add delta theta on here, keep r the same, so we're still r away, This now is going to be at the point r comma theta, so that's delta theta. And then if we close this out to the next point and do an additional delta r there, then we have this point's going to be r plus delta r, theta plus delta theta. And we end up getting something that looks like this. Okay, and so if you look at this little sector of a circle, what exactly is the area cut out here? And so the important thing is that if we are out r and we move delta theta across, how much did we actually move on the circle? Well, it's going to be r times delta theta there. Okay. Now, on the opposite side over here, this is then going to be, now we're r plus delta r away, so this is going to be r plus delta r times delta theta. And so that's r delta theta plus delta r delta theta. Okay. And so that's our box. That's our little bit of area. This is our change in A. By doing this, now if delta theta and delta r are small, then this over here is going to be very close to, well, if delta r and delta theta are small, delta r times delta theta, this is going to be very, very small. And so this outside side right here is essentially r times delta theta as well. Okay. And so, to make a long story short, this area right here is very close to a rectangle where the sides are delta r and r delta theta. And in fact, as delta theta and delta r get smaller and smaller, this is going to get closer and closer to a rectangle. And so what's the area of this rectangle going to be? Well, it's going to be r delta theta. Okay. So, cleaning this up, rather than our change of area being dx dy, right? Now our change in area, delta A, is r delta theta. And so then what's that saying about dA? dA, the r is going to stay there, delta r turns into dr, delta theta turns into d theta. Right? And as we take the limit as delta r and delta theta go to 0, these actually change literally into this. And so whenever we have dA or dx dy, dx dy is going to equal r dr d theta. Okay? So the takeaway from this, let's erase this, write this big. dA, so our measure for double integration, before we saw it as dx dy, this is what it is in rectangular. And so this is dx dy or dy dx. In polar, this is going to be r dr d theta or r d theta dr. This is what it is in polar. Do not forget this r there. That r is critically important. If that r is not there, then you are actually not doing the right integral. So you have to have this r here. It is r dr d theta, or r d theta dr. So wrapping up everything from that last slide, if we're starting off with the integral in terms of x and y, integrating in terms of dA, when we convert that into polar, so here we've thinking about this region in polar coordinates, and we're then going to be able to write it as f for x, we plug in r cosine theta, for y we plug in r sine theta, and then our dA is r dr d theta. We need to have that r there. That r is very important. Okay, so let's go back to the integral that we had right at the beginning of this video, and let's work it out now that we have everything that we need. Okay, so call our region here was split between two lines. So we have y equals x, and then we have y equals x times the square root of 3, and then we're inside the circle of radius 1. Okay, so what are our bounds here? Well, we saw before y equals x, this corresponds to y over x equals 1, and so that's tangent of theta. Tangent of theta equals 1, means theta is pi over 4. What about y equals x times square root of 3? Well, so this means y over x equals square root of 3. And so if we have square root of 3 equals tangent theta, that means that theta is equal to pi over 3. When theta is pi over 3, then tangent of theta is square root of 3. So our bounds for theta are going to go from pi over 4 to pi over 3. And then for r, well, 0, the origin is included in here, and so our r values start at 0, and they go out. For any theta in between here, they go out until we hit the circle, and that's at r is equal to 1. So our r bounds are from 0 to 1. Okay, and that's enough to get us our integral in terms of this. So our bounds for theta is pi over 4 to pi over 3. Our bounds for r is 0 to 1. So our integral is going to become, so x, this becomes r cosine theta. That's x. dA is r dr d theta. Our bounds here, they don't depend on each other, so it really doesn't matter what order we do the integration. So we can do r first. And so since we're integrating in terms of r first, r is going from 0 to 1, and then theta is going from from pi over 3, from pi over 4, to pi over 3. And now this is a really straightforward double integral to do. So I've got two r's on the inside, so let's put them together. This turns into r squared. We're integrating in terms of r first. So integrating r squared is going to give us r cubed cosine of theta over 3. And our r values are going from 0 to 1. And then whatever we get out of this, we're integrating from pi over 4 to pi over 3 d theta. Okay, so plugging in 1 for r there is going to give me 1/3. Plugging 0 in for r there is going to give me 0. And so this is becoming 1/3 cosine theta d theta from pi over 4 to pi over 3. And so then working that out, I get 1/3. The integral of cosine is sine theta going from pi over 4 to pi over 3. So sine of pi over 3 is square root of 3 over 2. And so we have square root of 3 over 3 times 2 is 6, minus sine of pi over 4 is 1 over square root of 2. So we're going to multiply that by 1/3. And there's our answer. And so, the big takeaway here is that by converting this into polar coordinates, rather than having to do this as two separate integrals, breaking the region up into two parts and doing two separate integrals, we were able to do one nice, simple integral that was very straightforward to do. And we get our nice answer. So that is all for this video. I will see you again soon.